class, I actually put the answers up for the problem I was doing and got fouled up with, which just goes to show you I can make a mistake on anything at any time, so keep your eyes on it. I want to go through several problems today, and I'm going to start by doing the one I messed up with. Is 22, is that right? Now, I'm going to do it my way. Did anybody notice the solution I posted earlier today? Anybody see it? I do my stuff on MathCAD. I don't know if you ever use this. I'll give you a secret. I'll tell you the secret. MATLAB is fantastic for prototyping. It means the first code that you write before you port it into a basic code like C or C++. MATLAB is fantastic. But MATLAB's strength is in doing matrix equations, and because of the immense amount of toolboxes MATLAB has. MATLAB has a fee. Some people, some companies, especially small companies, don't like fees. So they use either Python or Octave. Octave is virtually the same as MATLAB, but a little slower, actually a lot slower in some cases. Octave is free. The word free means a lot to people that have small companies. It doesn't get any better than that. And now Python is free too. Python is a little more cryptic. Both of them will do the job. I'm telling you that now because you guys are going out into the real world soon, and you're going to have to know certain things. Now, all those three are great for doing things, heavy-duty mathematical calculations. If you want to see something where what you see on the screen is what you get, and when you change any little thing, it'll change everything involved, all the equations. You don't have to rerun the code. Try MathCAD. There's a free version. It's called PTC MathCAD. Has anybody here used it at all? Nobody. Well, I'll tell you, I was told about this in like 87 or 88, and it has been a godsend for me. And you can do your homework with that. I mean, you need to know how to do it on a calculator. I'm just gonna love it. I can do 20 problems on that in the time it would take me to key my calculator for 2. That's how good it is, and I'm not understating it. And I'm not a salesman. I don't own stock in a company. I'm just telling you, that's a tip from me to you. Now, I put the solution for this problem up with a MathCAD solution. I'm going to go ahead and just do this thing. This is going to be 622. Someday, they're going to make markers that work. That one's not good either. That one will work. So for this, we have this voltage, and this is the way I would do this problem, now that I have a little time to think about it. All right, let me go through this, and I want to tell you how I would do it and what I recommend. They gave you a source voltage of V. They didn't say what it was. Then they say the output voltage here is 2V. That's the condition. But 2V is caused by this, right? The last thing you worry about is this. Don't worry about it. So what we're going to do when we write the equations, we're going to write them in terms of V. But I'm going to tell you the real trick, so you don't have to worry about some symbolic matrix manipulation. Here's the trick. Let this be 1 volt, which makes this 2 volts. Follow me? This is just going to be 2 volts. All you take the V away. Follow me on this, class? If the input is any value, the output is twice that value, no phase involvement at all. And if that's the case, the currents, I1 and I2, will scale proportionally. Do you understand that? That's all we care about. We can get the value of Jx very easily. Now, follow me on this one. That's I1, this is I2. Now we're going to go ahead and I'm going to put up what V1 and V2 are first. I did this last time. but I did this in a way that I think may have been a bit confusing. That's I1, this is plus to minus V1, and this is plus to minus V2 there. So V1 is equal to J omega L1 times I1 is the starting point, right? But we don't have an omega and an L. What we have, but yeah.
Shouldn't V2 be on the
J2
branch?
This is 1 volt, that makes this 2 volts.
No, it's like the
No,
other
the
inductor.
For the inductor too?
It's what?
The
V2.
other inductor.
You label Z1 and V2.
Instead of being on the center branch.
I have just a single inductor, is there? Where's the other one?
No,
J2 at top.
J2 up top.
you,
You labeled V1 and V2 across the same thing.
Sorry, this is V2, I'm sorry, this is V2. You're
Yeah.
right, V2 here plus one, I'm sorry about that, that's plus or minus V1, that's right, my bad. Alright, now, when I do that, I'm gonna just put what V1 is right here. So it's gonna be this self-impedance, J2, it's times the net current flowing down, which is I1 minus I2. So it's going to be J2 times I1 minus I2. It has to be the net current flowing in this direction. And everybody follows me on that? Then it's going to be plus the mutual impedance, which is J1, times the current flowing here, and that is just I2. So that's V1. V2, on the other hand, now I always try to put I1 as the first term, so it's the mutual times I1, right? And the mutual is J1, right? And it's times the actual value of the current flowing here, which is going to be I1 minus I2, or it will be the same as the term right above it in terms of what that will be, right? Normally it's just I1. Plus, then it's the self-impedance, and that is J2, is it not, class? Is that problem? That's J2 times I2. Those are the two values. Now what I'm going to do, I'm going to simplify this even more to make my life a little easier. When I look at this one, you see I have just JI1 here, right? And then I have minus JI2 or minus J2 plus J or just minus J. So I'm going to make this minus J, right? Get rid of that and just put it this way. Do y'all follow me what I'm doing here? I'm trying to just simplify the equation so they're easier to deal with. Everybody? Then I'm going to go ahead with this one and do the same thing. And I have JI1 here. I'll leave that alone. Then I have minus JI2 plus JI2 or just JI2. Do you all agree with me? So I get rid of this, and it looks like this. Just JI1 plus JI2. Do you all follow me on this, class? I prefer you do it this way. First get that right, and then go through the equations, because sometimes in the middle of trying to figure out all the things that are added, you're going to make a mistake. Now, what I'll do is start the loop, go around the loop right here. Okay? And I'm going to go clockwise around the loop. When I do this, I get a voltage increase of 1 volt. Do you agree with me, class? Because I made V 1 volt, didn't I, class? So I've got 1, right? And then this is going to be a voltage drop here, right? You all see what I'm doing, don't you, class? So it's going to be minus just 1 times I1, or minus I1. And then it's minus V1 equals 0. I'm going to go through it slow because I messed this up. Do you agree with me? Here, at this point, I'm going to do one thing. I'm going to take 1 to the other side, and then I'm going to get rid of the negatives, okay? So if I do it that way, I get this, going slow, and now I'm going to replace V1 right there with the V1 in terms of the currents, the unknown currents. So now I get I1 plus V1, which is going to be plus 2JI1 minus JI2 equals 1. The only thing I've done here is replaced V1 with the V1 on top. Everybody? And then I'm going to go ahead and just group the coefficients. So if I look at I1, it's going to have the coefficient 1 plus J2. Do you agree with me? I1 and I2 has a coefficient of minus I2. Now at this point, I tell you to do this and you'll thank me for it. Put a box around it and just label that equation 1. You won't go wrong doing it this way. Everybody got it? Now we're going around the second loop. The key is, because I made that 1 volt, this is 2 volts. You can forget the ratioing business then, all right? It is 2 volts. Do you follow me? So when I do the second one, I start here, and I'm going to go, that's a voltage increase of V1. Do you see that? So it's going to be plus V1. And then it's a voltage decrease of V2. Can everybody see that? A decrease, minus V2. And then it's a voltage decrease of 2. Do you all see that? Everybody? Okay. So it's minus 2 equals 0. And again, the only thing I'm doing is making sure I carefully go around the loop. Not in a haphazard way this time. Now, what I do is I'm going to take 2 to the other side. Okay? Everybody with me? Add plus 2 to both sides. And now I get this. You all agree with that? Make sure you do, right? Next, after that point, now I stick in for V1 and V2. So V1 is equal to 2, really J2 times I1 minus JI2 minus the quantity V2. Well, that's V2. So it's JI1 plus JI2 equal to 2. Just so everybody's got, you all with me? When I do this, next I group the coefficients of I1, right? And I can see here for I1, I have J2 and minus J are just J, correct? So I have, for I1, I have JI1. And then I have minus J2, from minus J, and minus J is minus 2JI2 equal to 2. Take a look there. Do you all agree with that, class? Can you all see this okay, everyone? All right, then box that right there. We'll call that number 2. Agreed? Now, I'm going to erase that circuit to give myself a little more room. And now I'm going to put it in terms of a matrix and actually solve for I2. That's the value I care about, not I1. So I have this in terms of a matrix, and it's going to be 1 plus J2, and then minus J. Then I have J, right? And then I have minus 2J times column vector I1, I2 equal to 1 and 2. Y'all agree with that? Now that I have that, I'm going to solve for I2. I don't care about I1, I care about I2. Your calculators can do this directly, can't they? But really, what you need is the determinant of this, first by itself. Actually, do it on your calculators. I'm not going to do Kramer's rule here. I can do it with Kramer's rule. And the solution manually does it with Kramer's rule. I haven't used Kramer's rule, honestly, in any place but this course in the last 15 years. It's nice to teach you what your calculator's doing, but frankly, your calculators can do it a lot faster. So what do you get for that? For I2. Give me a magnitude, an angle, or a real imaginary, it won't matter. If you have your calculators, try this one, it's good.
just one.
Looking for I2, right?
Couldn't hear you?
Just one.
I got
I'm on I2 now.
one angle 90 for I2.
Alright, one at an angle of 90 degrees, or simply J, correct?
Yeah.
Please watch. Now, they want the value of that impedance, JX, right? So the impedance of the output was just JX. And what is that, or minus JX, pardon me, right? And what is that? Well, that's V out over I2, isn't it? You with me? What is V out? 2 volts. So it was, this minus JX is 2 volts over I2, which is just J, correct? Y'all see that? Take 1 over J, you get minus J, don't you, class? That means X equal 2. I believe that's his answer. Tell me if it isn't. Isabel, is that right?
I'm not sure.
Can anybody look up the solution? I believe it is, but that's the way to do it. Now, I'm telling you the trick. You could do it with a ratio the way he did, but it's more work. If it works for one set of voltages, it worked for all of them. Is that it?
It hasn't pulled up yet.
Yeah, it's 2.
It is too? Thank you. I did that one, and I just wanted to show you the right way to do this. Now, when you have circuits where you don't have this different currents in the primary, in other words, you have some of the primary current flowing in the secondary, then you have to go through the analysis the way I did it. But usually, they would give you an input voltage and we want an output voltage or current. That's normally, it's analysis, it's not synthesis, and that's for electrical engineers to worry about that kind of stuff, not you. All right, I wanted to do that one. Now, before I get on to the problems I have for you, does anybody have a problem they want me to do? Yes? Somebody say yes? If you, I mean, please, just, I'll be more than happy to help you. But I've got some problems for you because here, last time I did what? I gave you things about transformers with turns ratios, not coupled circuits. I'll show you how a coupled circuit becomes a transformer a little bit later. But these are really important problems. Now you can get confused really easy with some of this stuff. So next, now we're not talking about, yes?
Were you still, you moving on, or are you gonna do problems?
I was gonna do a problem, but do you have something special for me to do?
Not specifically, I was gonna say.
All right, then I'd like to do 629. If you're looking on your phone or your laptops or your tablets, you can probably go there. I'm trying to do the problems that are not gonna be super crazy at first, just basically trying to step up the level of difficulty and some of the theoretical aspects of it. Now, one thing about all these problems, and from here on out, you have to use all your bags, all the tricks in your bag to try to solve something. Remember I told you always try to do source transforms to get it down to just one current in the primary if possible. Always make your life easy. Don't make it hard. It'll get that way it's on its own. For 629, he forgets to put a dot in the actual original problem statement, the problems. But on the output side, in his solutions, he does put the dot. For this one, he has this. And this is a type of problem you would see on an examination and a quiz. So he has IS here, and he has, make sure this is right, by the way, in your book, 6 here. I have an old generation book. And this is minus J2, and then he has an iron core transformer here. The reason you know it's iron core is he has this, and he has a dot there in the primary, and this is I1. And then he has, on the secondary, this is important that you see this, the dots on the other side. Now, it wasn't in my book that way. Does yours have, in your solutions, some people have bought the book, I know they have, and some people are looking at a book that's rendered online, but it's important to note that the dot is on the other side. It's not at the same side of the transform, that happens. Anybody looking at this stuff in the book?
The book for 629 says it's about the top.
It does say on the top on yours?
Yeah.
And I'll put it at the top of mine, and we'll just do it that way. All right, we'll put it at the top, that's all right. It probably isn't, I'm probably wrong, but one of them has a dot wrong. 2 to 1, and then he has J2 here, right? And then he has 1, and he has minus J1 here. And he's got V out. That's 12 volts. The answer's wrong for this one, I believe, unless, is this plus to minus V out here, right? And he has 12 volts at 0 degrees. Do you see this, class? Everybody with me on this? All right, so that's the circuit. I'm going to call this I2. I want you to notice I2 has to go in the dotted terminal. I think this is the one that in the solutions manual, he has the dot on the other side. I'll put the dot there and I'll show you why. This is going to be a little different. Now, be attentive here. 2 to 1 means there's twice as many turns as the primary as secondary, right? That means the primary voltage is 2 times that of the secondary voltage. The primary current is only 1/2 that of the secondary current. It's important that you see that. Everybody with me on that? You have to understand what turns ratios mean. And I'll put them up there in a second. As a matter of fact, let me just do this. I know that V1 over V2 is equal to N1 over N2. And N, or the primary over the secondary right there, is going to be 2. Follow me on this? So that would be 2 to 1, right? Now, with that in mind, so V1 is equal to 2 V2. And as soon as I see that, if the ratio twice as much voltage is on the primary as the secondary, I know twice as much current will be on the second, or on this one, the secondary, it's going to be equal to 2I1 is equal to I2. All right, because I2, less turns, more current, all right, think of it that way. Now, what he actually says is this output voltage is given like that, and he wants this current, and only this current. So listen to me carefully. You can see what you need to do. You ask yourself, well, what do I need to get that current? Well, I need current I1 in the primary, right? Well, that current is what? That current is simply 1/2 the current flowing here, isn't it? If I find the current flowing here and I divide by 2, I have it, right? Do you all follow me? Now, yeah?
Would IS be the same as I1?
Has to, right?
Okay,
Flowing that way, correct?
just making sure.
I mean, you see it, don't you? It has to. All right, now, if I come here, what is I2? Well, if I have a voltage over an impedance,
Is that V1 over V2?
when you look at this, what does turns ratios mean? Normally it's what? N1 over N2, right?
Yes.
Now look at this. He says there's 2 times as many turns in the primary as there is the secondary. So N1 would be 2 to 1, or it'd be 2, right?
Yes.
All right, that means 2V2 is V1. Just multiply by V2. Okay. Now, coming over here, you all see that we can get the current flowing here. That is not I2, but can we get that current? We've got a voltage across an impedance. You all see we can get this current. What is this current right here? I'll just call it I prime. That's going to be equal to 12 at an angle of 0 degrees divided by 1 minus J1, right? Just give me that value. You all agree that's the current there, right? It's not the current we want, but it is going to, at least it's the same magnitude, but not the right sign. So what is this going to be? Anyone? 8.45, something like that?
8.48 at an angle of 45.
8.48 at an angle of 45 degrees. Now you'll notice that current is flowing what? Down, or it's flowing opposite of I2. Do you all see that? So I2 is just the negative of that. Or you can add simply or subtract 180 degrees to this and you get the right answer, all right? You can put a minus sign there, or add or subtract 180 degrees, right? Probably subtract 180 degrees and give me, therefore, what I2 is. I2 is just equal to minus I prime, and what is that? Take 145 and subtract 180. Isn't that minus 135?
Yeah.
Sure. So this is going to be 8.48 at an angle of minus 135 degrees, amps. That's I2. I1 is simply I2 divided by 2. Do you all see that, class? Right? I1 is going to be just half that, based on this equation right here. Correct, everyone? How many see this right here? Are you with me? Now, his answer's wrong in the book. I'm almost positive of it. So if you take this I2 right here, I'll talk to him afterwards, I2, and I say that now I1 is simply I2 by 2, that's going to be what? 8.48 would be 4.24 at an angle of minus 135 degrees amps. And that would be I1. Look at his answers if you can. You'll see he has the right magnitude, wrong angle. Take a look. Y'all see it there? Can you review that as well? Or somebody, can you get the solution to this? This is 629.
It's, he has 4.24 at an angle of 45.
Yeah. What he did was one thing. He assumed that this was the dot down here. That's what he did. He had it drawn that way in the solutions manual, but in the book it's this way. And at least in my book. Go ahead.
Why did you choose the opposite strength for I2 instead of just using the voltage and the resistance
Well,
for I2?
there's one primary reason. Current always flows into the dotted terminals for those equations to work, right? So I needed I2 this way, right? What I had was a voltage and an impedance. If I take the voltage divided by the impedance, I get the current flowing this way, don't I?
I don't know, I thought the current was here.
Now think about this and just make sure you're straight on this one. If you have an impedance Z and a current I, and this is plus to minus V, that I is equal to V divided by Z. Now you'll notice the current flows into the positive, out of the negative terminal. This is plus to minus, current would be flowing this way.
Okay.
Make absolutely certain you know that, yeah?
What happened to change the angle from 45 to negative 135?
Well, technically it was, I wanted to put a minus sign in front of it, right?
Yeah.
But what is actually adding a minus sign do? It just changes the phase by 180 degrees. So I added 180, or I actually subtracted 180 from it. And that's the thing you keep in mind always. Whenever you're talking about polar numbers, if you want to make the number minus what it is, you just add or subtract 180 to it. Yeah, go ahead.
And you also just put a negative.
You can do a negative too. That's absolutely legitimate. But in polar, now I want to just say this. I'm not a stickler for this, but there are those that are. Normally, the first term is only a magnitude. The negativeness is all absorbed in the angle with polar numbers. Almost always. Of course, I'd let you get away with it, but I'm going to tell you that there are some of those out there that are in your majors that wouldn't. And I know. You've got a few in ours. Y'all are okay with this class? Yeah.
On problem 4.24, it has a ratio similar to this of 2 to 1. But their end value, they have 1/2 for that.
Well, that's probably, if you're going 2 to 1 this way, it's 1/2 the other way. Remember, when we took the current there, we divided by 2 or multiplied by 1/2 to get the current in the primary. I'm going to just tell you, these ratios are the only thing that you have to worry about right there. Okay. Everybody okay with this? Yes.
Is, the reason why we don't have to use any mutual inductances is that.
There is no mutual inductance. This is a transformer problem, not a coupled circuits problem. This is transformer, it's turns ratios. See, what I didn't get to tell you, and that comes at the next lecture, is this. If they have very, very good coupling, all right, then what you end up with is that the primary and the secondary, really what happens is the mutual is equal to the square root of L1 times L2 times a factor K. If K is equal to 1, and this is something you're going to have to take on faith, then in fact, you don't need to worry about a magnetically coupled circuit. You have two distinct things given by these equations. But I can show you that with magnetically coupled circuits, or magnetic circuits, the way we drew them, if it's strongly coupled. In other words, if you take the primary, take L1, L2 square root, if that is equal to M, and it's strongly coupled, then these equations hold. But you see with a magnetically coupled circuit, they don't even mention the turns, right? It's not even mentioned, right? Because they're
Is that why it says like ideal?
this is an ideal transformer, but almost all transform equations don't use the mutual coupling equation. You don't have J omega L1. You don't even know what L1 is, frankly. You just use these equations. Yes?
Could, like, just theoretically, if that was a mutual inductor, could you also like have that where there's another inductor that's just kind of part of the impedance?
Well, if there's
Like,
mutual
it's not a
inductance,
dot.
then you're gonna have J omega something here, or J omega L1, J omega L2, and then J omega M there, right?
Okay, no, I'm just saying, like, there wouldn't be like an extra inductor in those problems, right?
You mean this?
Yeah.
You could put inductor in. There's
Okay,
no
so
reason
then
why
it
not.
would just be when you just treat it like the impedance.
You could put, yeah, in any of these circuits, when you have either coupled circuits or transformers, you can put any elements on that side and any elements on that side you want, okay? There's no law against it. Yeah,
So why is I2 equal to negative I prime? Because wouldn't the inductor J2?
remember I wanted the current going this way, right?
Right.
What did I find? The current going in the opposite direction. Therefore, I2 is just minus the current I found.
Wouldn't that inductor at the very top not add an impedance?
Doesn't matter. If you're talking about current is the same in all these components, isn't it?
Okay,
The inductor has nothing to do with the value of current.
okay.
Got me? All right. Y'all see this? How many do right here? You gotta do a few more problems before you really start feeling comfortable with this stuff, though. And the next problem is gonna be a little different. The next problem is involving, now we're getting into the more horrifying aspects of this, where it's a bad word, but it was Halloween history. We're gonna be talking about now when we have a load, when we talk about power, right? And this is gonna be problem 632. You have all the tools to do this one. So, but now he's using VRMS. So I'm gonna show you this one, we're gonna do it together. Make sure you see this. This is 632. Now on this one, you're gonna have to help me. Is the dot here on yours or here, or is it left out?
Left out, they just have the positive and negative.
All right, this one is again one that they have the dot, Dave Irwin intended the dot to be down here for V2. And that's 2 ohms. And then you have a load here, but this load is in power, so it's saying it's 500 watts. And the power factor is equal to 0.8, only it's lagging, lag. And there's a voltage plus to minus 100 volts RMS. This is the difference. Everything else has been in peak value. Now it's RMS. Do you all understand? So now we're into the range where we're talking about power. And what he wants is this. He wants this value of voltage. That's his goal. We're going to put the value of that voltage in both RMS and peak units, all right? Just to be clear. Now please watch me. You all see that? You're looking at me like, okay, trust me. All right, now when I come here right away, if I have 500 watts, it does say 500 if you look at the problems, right? That means 500 watts is equal to actually VRMS times IRMS, these are magnitudes, times the power factor. Right? VI power factor is equal to wattage, correct class? It's the projection of the complex power on the horizontal axis. It's real power. So to get IRMS, I take 500 and I divide it by V, which is 100, and then I divide it by 0.8, And now I get the current, but the current I'm getting is this current. And it happens to be I2, if that dot's at the bottom. Do y'all see that, class? That's flowing into the dot. What is this value in magnitude, anyone? It's 5 over 0.8. Is that like 6, 7?
6.25.
Yeah. 6.25. And that's really amps RMS, right? And what's the angle? Now, it's not stated, but you can assume this at 0 degrees, because it's the voltage considered the load voltage. Unless it states an angle there that's different than 0, you have to assume 0. Now, how do I get that angle? Well, I take the inverse cosine of 0.8. It's like 36 degrees, I think, 35 something, right?
36.
36, whatever, and then it's negative because it's lagging, right? So it's going to be minus 36 what? 0.86. And that's degrees. That's IRMS through there, and that is also I2. Now here, I didn't get this. Can somebody just tell me the turns ratio? Is it 2 to 1 or 1 to 2 something?
1 to 2.
It's 1 on primary, 2 on secondary, is that right? All right. Right away, they're after this voltage, right? Now hear me. We're going to need both the current in here and the voltage. Here's why. I need to get the voltage there, and the only way I get the voltage there is knowing the current on the primary. The voltage here is gotten by knowing the voltage there, correct, class? So please watch this. Just everybody take a good look at the problem. Make sure you know what I'm about to ask. You good with this? First thing I'm going to do is calculate this voltage right here. Now you'll notice I have I2, right? So this voltage V2 will be equal to I2 times 2 plus 100. And it will be RMS. Does everybody see that? Give me a show of hands if you do. Right? If you're looking at me cross-eyed, I don't believe it. Think about it. If current goes in here, isn't it plus to minus here, right? So if we start here, it would be an increase of 100, then an increase of 2 times I2 would be V2. Do you all see that? Show of hands again, make sure I see. All right, you good with that? Whenever I look at people and they're looking at their laptop, then at me, and then they look like, I don't know if you're worried about the laptop problem. Is that what it says, or I'm talking to you? Is it? Okay, whatever that. You're not following this, or? Never mind. All right, wasn't meant to be a trick question. What is this equal to then? You've got I2 here. Notice it's polar though, all right? You can't just take 6.25 times 2. You've got to add these two things up as polar numbers. Follow me? What do you get? I need to know. Magnitude and angle. I know you guys are good at this. You probably hate punching in too. It's Friday, I'm tired. You're tired?
So tired.
It's been a long week. I've had more to do this week than I can think.
110.26.
All right, so V2 is 110.26 at what angle?
Negative 3.9.
Is that right?
Yeah.
3.9 degrees, great. If that's V2, no, 2 to 1. The primary has 1/2 the voltage of the secondary. Does everybody follow me in the way I'm talking about this? We could write the turns ratio equations every time, but you've got twice as many turns on the secondary as this primary, twice as much voltage, all right? That means voltage V1 is just V2 divided by 2. Now here's the kicker that I didn't say anything about. You'll notice this V2 is what? See that? Isn't that right? Because the plus is always at the dot, isn't it, class? Plus to minus. The V2 that I actually put there is what? Negative that, isn't it, class? How many see this? So what I'm going to do to correct that is take this and add 180 to it. You follow me? Then it'll be right. This V2, this is actually minus V2. Add 180 to that, and what do you get? I could put a minus sign there, as he said before. What do you get? That's going to be what?
176.1.
0.1 degrees. And that's fine. All right. So that is V2. Do you follow me, everybody? Remember, you need the plus to minus voltage of V2. I had the plus here and the minus there, and that's what he does in his solutions, I think, but I'm not absolutely certain. So now that's the right value for V2, and V1 is just half that value. So that's what? That's 55.13 at an angle of 176.1 degrees. Agreed? Everybody? Now, if we have that, if I want the primary current, you'll notice I2 is going into the dot, right? Therefore, I1 here will be correct. I mean, the value will be given by just what? Well, it's 2 to 1, right? Twice as much voltage here, 1/2 as much current as the current here, correct, class? So now the current is going to be 2 times I2. Do you all see this? So it's 2 times I2, or I1 here is going to be 2 times I2, and I2 was 6.25, so this is 12.5 at an angle of minus 36.86 degrees. So that's I2 or I1, right? You agree? And now to get VS, check his answers too. What is VS going to be? Well, here, do you agree that if I want VS, I start from here, it's going to be V1 plus 4 times I1. Do you all see that? So it's going to be V1 plus 4 times I1. That's I1. And this is V1. So if you take 55.13 at 176.1 plus 4 times that, tell me what you get polar numbered, please. Remember, you got to add these as polar numbers, huh? And class.
I got 100.8 at an angle of negative 19.6 degrees.
That's volts RMS. 100.8, did you say?
Yes.
0.8, go ahead.
At an angle of negative 19.6.
And that's RMS volts. Now, in his book, I don't know if he puts it in RMS or not, but I think he's got the wrong sign for one of the currents. What does he have? Does anybody know? This is problem 32, 632. Look for the value of VS and tell me.
It's negative 100.8 at negative 19.6.
And I'm going to just say what he did was he messed this up right on that side if you look through the solutions. You can, yeah.
His V2 switched, so he has a plus on the top of V2.
Isn't the dot in the bottom of the book?
There's not a dot, but he has plus and minus, plus on the top.
Yeah, but has he got a dot? I tell you, I have an older book, and if the dot's on the bottom so that our current flows in, this is the right answer. If the dot's on the top, I2 will be negative that value. But this is the way I've showed you to do this is the correct procedure. Do you follow me on this, class? Now here you've added the element of power into this, right? And our voltage here is actually a peak, or an RMS voltage. If you wanted the peak voltage, what would you have to do? Somebody, did you say it or not? How many know? Anybody know? Multiply by square root of 2, right? The whole idea is the RMS is really the effective voltage. It's lower than the peak value. Peak value is the top of the sinusoid, right? The very peak level possible. So you multiply it by square root of 2, or 1.414. Follow me? So it would be about 141 volts is really what I'm talking about. That's RMS, but they want peak. Your wall voltage here is about 117. It's usually labeled as 120. That's an RMS value. The peak value is close to 200 if you multiply 120 by square root of 2. So if you actually get a scope, when you take your an oscilloscope, you know what that is, and you measure it, you will see it bounce up and top almost to 200, plus or minus 200, almost. Just take square root of 2 times 120. What do you get? Okay, about 170. and you'll see the thing, because this is a typical thing, when you measure, you'll see it goes plus or minus 170 on an oscilloscope. All right, that's another good problem. Now, I've got 3 minutes, and I'm going to tell you, we're closing, about to shut the door on this chapter. And we've done a lot of stuff. We've done, in the chapter 5, we've done 3-phase power. Here in this chapter, we've done magnetically coupled circuits and transformers. The last thing I'm going to do is show you how one becomes the other when they're strongly coupled. I didn't do it yet, but here, for the Monday quiz, you're going to get the last couple of lectures. So magnetically coupled circuits, transformers are what you're going to have to be up to date on. And I'm going to give you a few more problems. Now you got all the solutions, right, in chapter 6. You got all the problems. If you see something where the solution manual doesn't agree with the problem statement in the book, don't flip out, all right? Just make adjustments. I think there's been a couple of mistakes there. I think a grad student might have got a hold of some of this and done it. Not Erwin. Erwin doesn't make mistakes, but very rarely. The last bit of homework is going to be from 6:30 to 6:33. So there's 4 problems, 6:30 to 6:33, and I can tell you right now, they're not tricky if you do them the way I said. And first, these are transformer problems, so write the equations for output to input voltage, output to input current. Remember, current goes into the dot, voltage is plus at the dot. And I've held you up before, so I got about 149. Are there any last questions before we break? Have a great, yes, sir.
Quick question, so I know that, peak voltage is vertically times VRMS, is that the same for current?
Yeah, they're both the same. Now, but that's the key thing about this is that both current and voltage, if they're sinusoidally varying terms, right? They have a steady state frequency. The peak value is the square root of 2 greater than the RMS. Same with current.
What about on that